Well, this is the video where we are actually going to look at some practical situations which are examples of simple harmonic motion. So, for our first point, we're going to have to remember one or two things about simple harmonic motion examples. The first one is that the displacement x should always be measured away from the equilibrium position. This obviously means that you've got to find the equilibrium position before you do anything else in an example. In order to set up the SHM equations, it's absolutely crucial that we prove that the displacement satisfies the equation x double dot equals minus omega squared x. And that requires Newton's second law at a general time t. And if we're going to do that, we obviously need a good, clear diagram at a general time t. Remember on your diagram that once you've put on the positive direction for the displacement, then the acceleration x double dot should be in the same direction. So the displacement and the acceleration have the same positive direction. So for our first example then, we've got a light elastic spring of natural length 1.2 meters is attached to one end of a fixed point O, and at the other end to a particle P of mass 0.5 kilograms. The particle hangs in equilibrium 1.4 meters below O. We've got to find the modulus of the spring. The particle is then pulled 0.3 meters down from the equilibrium position and released from rest. We have to show the subsequent motion is SHM and find its period and amplitude. And we have to find the time when the particle is first 1.25 meters below O and the velocity of the particle at that particular instant. So, part A, we've got the particle hanging in equilibrium 1.4 meters below O, and we've got to use that to find the modulus of the spring. So there's our equilibrium diagram. We can add the forces, so there's the weight of 0.5 g and the tension in the spring. And for equilibrium, we know the resultant force must be equal to 0. So the resultant force upwards is T minus 0.5 g. In other words, now we know from Hooke's law that the tension in a string or a spring is lambda times by the extension divided by the natural length. So the tension is lambda times by 0.2 divided by 1.2, and the tension minus 0.5 g has got to equal 0. So I've got lambda is 4.9 times by 1.2 divided by 0.2, which is 29.4 newtons. Moving on to part B, we have to show that the particle, when it's pulled down by 0.3 meters from the equilibrium position and then released from rest, will execute simple harmonic motion. So there's my t equals 0 diagram, and then crucially I need to do a diagram at an arbitrary time t. At my arbitrary time t, I'm showing the particle at a distance x below the equilibrium level. So I'm regarding movement downwards from the equilibrium level as being my positive direction for the displacement. And if that's the positive direction for the displacement, it must also be the positive direction for the acceleration. So we've marked X double dot on. Putting the forces on, I've got the weight and the tension. So I can now apply Newton's second law in the direction of the acceleration. So I'm going to apply Newton's second law downwards. We obtain 0.5 g minus t dash is the mass 0.5 times by x double dot. 0.5 g is 4.9. T dash is going to be lambda, which is 29.4, times by the extension of the spring at this particular stage, which is 0.2 plus x, divided by the natural length of the spring, which is 1.2. So we've got 4.9, take away 29.4 times x plus 0.2, divided by 1.2, must equal 0.5 times x double dot. So, simplifying that out, 29.4 divided by 1.2 gives me 24.5. So I've got 4.9, take away 24.5 times x plus 0.2, must equal 0.5 x double dot. Multiplying the brackets out, we've got 4.9, take away 24.5x minus 4.9 equals 0.5 x double dot. In other words, we've got minus 24.5x equals 0.5 x double dot, or x double dot is minus 49x. So, at this stage, we have the standard equation of simple harmonic motion, x double dot equals minus omega squared x, with omega squared equals 49, which means that omega must be equal to 7. We know that the period for simple harmonic motion is always 2 pi over omega, so in this case that is 2 pi divided by 7, which is just a little bit less than 0.9 of a second. The amplitude of the motion, well, we know that when t equals 0, the particle is 0.3 meters below the equilibrium level, and it's at rest at that point. So 0.3 meters is the maximum displacement of the particle away from the equilibrium level. So we've got the amplitude of the SHM is 0.3 meters. Finally, we've got to find the time when the particle is first 1.25 meters below O and the velocity of the particle at this particular instant. Now, if OP is 1.25 meters, then that means that what we want is the value of x has got to be minus 0.15 meters. Okay, because the equilibrium level is 1.4 meters below O, we need to have the particle, therefore, 0.15 meters above the equilibrium level, but we've been saying that the positive direction for x is below the equilibrium level. So 0.15 meters above the equilibrium level corresponds to x equaling minus 0.15. We all know that when t equals 0, we've got x equals 0.3 and v equals 0, which means that we can just say straight away that the solution of the SHM equation is the x equals a cos omega t format, because we're starting at an extreme point. So we've got x equals 0.3 cos 7t. So what I want is minus 0.15 to equal 0.3 cos 7t. In other words, I need minus a half equals cos 7t. The first positive angle, which has got a cosine of -1/2, is 2 pi by 3. So we've got 2 pi by 3 must be equal to 7t. So t must be 2 pi divided by 21. The velocity at this particular time can just be obtained by differentiating. So we know that v is dx by dt, so that is going to be minus 2.1 sine 7t. And if we put t equals 2 pi over 21 into that, we obtain v equals minus 2.1 sine of 2 pi by 3, which is minus 2.1 times root 3 over 2, or roughly minus 1.82 meters per second, which means that at this particular time the particle is moving at 1.82 meters per second in the negative direction, in other words, upwards. For our second example, we have AB and BC are elastic strings, each of natural length 1.5 meters and modulus 19.6 newtons. The ends A and C are fixed to 2 points with distance A 5 meters vertically above C. Each string is connected at the point B to an object of mass 0.4 kilograms, which is resting in its equilibrium position. So the first thing we have to do is find the equilibrium position of the particle. Then the particle is pulled down 0.7 meters and released from rest. We have to prove that the subsequent motion is SHM and find its period and amplitude. We have to find the speed of the particle as it passes through a point 0.35 meters below the equilibrium level. And we need to state two assumptions that have been made in the course of answering the question. So we're starting off then trying to find the equilibrium position. So there's my diagram. So I've got A and C, which are 5 meters vertically apart. We've got B sitting in equilibrium somewhere between A and C. And what we're going to do is we're going to suppose that the point B, the string AB has an extension of E when B is in equilibrium. Now, if that's the case, then we have the length of AB is 1.5 plus E, which means that the length of BC must be 3.5 minus E, which means that the extension of BC must be 2 minus E. So just check that you're happy with that extension having to be 2 minus E. Onto the diagram now, we need to superimpose the forces acting. So we've got 0.4 G downwards. We've got a force T in the string, so that's the tension in the string BC. And we've got a force S upwards in the string AB. So these are the forces acting on the particle B. So if we apply Newton's second law vertically, we know the resultant force must equal 0 because this is the equilibrium position. So that is S minus T minus 0.4 G equals 0. Now, for S, then we've got lambda times the extension of that string divided by the natural length. So that's going to be 19.6 times by E divided by 1.5. For t, again, we've got lambda times the extension of the string BC divided by the natural length. So that's 19.6 times 2 minus e divided by 1.5. And we've taken the 0.4g onto the other side. So we've got 19.6e divided by 1.5. Take away 19.6 times 2 minus e divided by 1.5 has to equal 0.4g. Multiplying this through by 1.5 and simplifying the left-hand side, we obtain 39.2e minus 39.2 must equal 5.88. In other words, solving that equation, we get e equals 1.15. So we now know the equilibrium level has E equals 1.15. So here's our diagram at t equals 0, where we've pulled B down by a further 0.7 meters. And if we've pulled it down by 0.7 meters, that now means that the extension of BC is only 0.15 meters. And we're going to release it from rest in that position. And then at time t, we're going to suppose that the point B, or the mass P, the particle P, is x meters below the equilibrium point. If that is the case, then the extension of AB is going to be 1.15 plus x, and the extension of BC is going to be 0.85 minus x. The positive direction for x in our diagram is downwards, so that is also the positive direction for our acceleration x double dot. Adding the forces onto this general diagram, we've got the weight 0.4g, we've got the tension upwards S dash, and we've got a tension downwards T dash. Applying Newton's second law now, downwards, we have got T dash plus 0.4g minus S dash must equal a mass, which is 0.4 times by x double dot. T dash is going to be 19.6 times by 0.85 minus x divided by the natural length, which is 1.5. S dash is going to be 19.6 times by 1.15 plus x divided by 1.5. So our equation becomes 19.6 times by 0.85 minus x divided by 1.5 plus 0.4g minus 19.6 times 1.15 plus x over 1.5 equals 0.4 x double dot. If we times through by 1.5 to clear the fractions, that now gives me 19.6 times 0.85 minus x plus 0.6g minus 19.6 times 1.15 plus x equals 0.6 x double dot. Multiplying out the brackets and also calculating 0.6g gives me 16.66 minus 19.6x plus 5.88 minus 22.54 minus 19.6x equals 0.6x double dot, which simplifies to minus 39.2x equals 0.6x double dot So we've got x double dot is minus 196 over 3 times x. So we've got the SHM equation with omega squared equals 196 divided by 3. Or if you like, that means that omega is 14 divided by root 3. Since v equals 0 and x is 0.7 when t equals 0, that's telling me that I'm at an extreme position of the SHM because v equals 0 and that the amplitude of the motion is 0.7 meters. This means that the extension of the string AB varies between 0.45 and 1.85 meters, whilst the extension of BC is going to vary between 0.15 meters and 1.55 meters, which tells me that neither string goes slack through the motion. So the Newton's second law equation we've got is valid throughout the motion, so we have got proper simple harmonic motion. The period of this motion is going to be 2 pi divided by omega, which is 2 pi divided by 14 upon root 3. So that is pi times root 3 divided by 7, or roughly 0.78 seconds. If we want to find out the speed when x is equal to 0.35, then we've got v squared is equal to omega squared times a squared minus x squared. So that is equal to 196 over 3 times by 0.7 squared minus 0.35 squared, which gives us 24.01 for the speed at that point. So the speed is 4.9 meters per second when the value of x is 0.35. In terms of assumptions that have been made, well, we've certainly modelled the object as a particle. We've modelled the strings as being light, and it's been assumed that neither string has exceeded its elastic limit. And we've certainly also assumed that there is no air resistance. Now for our third and final example, we've got A and C are two fixed points on a smooth horizontal table which are distance 3 meters apart. An elastic strength of natural length 0.6 meters and modulus 56 newtons has one end fixed to A and the other end attached to a particle of mass 0.4 kilograms. Another elastic string of natural length 1.2 meters and modulus 80 newtons has one end attached to C and the other end attached to the particle P. We've got to start by proving that when P is in equilibrium, the extension of the string AP is 0.5 meters. So here's our overhead view of the equilibrium position. If the extension of the string A to P is E, then because the natural lengths of the strings add up to 1.8 meters, the extension of the two springs must add up to 1.2 meters. So the extension of the string PC must be 1.2 take away E. Putting now the forces onto the diagram, we've simply got the two tensions because we're simply putting the horizontal forces on. Don't need to worry about the vertical forces in this question. So, Newton's second law, we've got T minus S must equal 0, resultant force equals 0, so T minus S equals 0. S is going to be equal to the modulus of the string, which is 56, times by the extension of the string PA, which is E, divided by the natural length, which is 0.6. whereas t is going to be the modulus, which is 80, times by the extension, which is 1.2 minus e, divided by the natural length, which is 1.2. So we've got t must equal s, which gives me 56e over 0.6 equals 80 times 1.2 minus e over 1.2. Multiplying up by 1.2 gives me 112e equals 96 minus 80e. In other words, we've got e is 96 divided by 192, which is 0.5, as required. So there's the equilibrium position, fully described. We're going to now move the particle 0.3 meters towards c, and also give it a small velocity of magnitude u towards c. So here's the equilibrium position. Here's the diagram when t equals 0. And then we're going to show the diagram at a general time t. And we'll suppose that at that general time t, that the particle p is x meters to the right of the equilibrium position. Remember, we've always got to measure our displacement away from the equilibrium position. Once we've marked that as being our positive direction for the displacement, that is also the positive direction for the acceleration. Adding the forces on, we've got the two tensions again. Applying Newton's second law to the right, we've now got t dash minus s dash must equal 0.4 times x double dot. Now for t dash, the extension now of the string PC is 0.7 minus x, and the extension for the string A to P is now 0.5 plus x. So t dash, to begin with, is going to be equal to 80 times by 0.7 minus x divided by 1.2, and s dash is going to be 56, the modulus, times by the extension 0.5 plus x divided by the natural length 0.6. So my resultant force is there on the left hand side, equals 0.4 times x double dot. If we times through by 1.2, we've got 80 times 0.7 minus x minus 112 times 0.5 plus x equals 0.48 x double dot. Multiplying the brackets out, we've got 56 minus 80x minus 56 minus 112x equals 0.48 x double dot. In other words, we've got 0.48 x double dot is minus 192x, or x double dot is minus 400x, which is a simple harmonic equation with omega squared equals 400, so omega equals 20. So we're going to have SHM with omega equals 20, provided both of the strings remain taut. Now that is going to be the case provided the amplitude of the motion is less than 0.5 meters. So we need the amplitude to be less than 0.5 meters. If we use the fact that we know when t equals 0, x is 0.3 and we've got an initial velocity of u, and the fact that we know that omega is 20, then the equation that v squared equals omega squared times a squared minus x squared tells me that u squared is equal to 400 times by a squared minus 0.3 squared. In other words, a squared is equal to u squared divided by 400 plus 0.3 squared. But we just said that we needed a to be less than or equal to 0.5 for it to be proper SHM, with neither string going slack. So, in other words, a squared has got to be less than or equal to 0.25. So we've got u squared over 400 plus 0.09 must be less than or equal to 0.25. In other words, u squared has got to be less than or equal to 64, which means that u must be between -8 and 8 meters per second. And if that's the case, then the motion is going to have period of 2 pi over omega, which is equal to pi by 10, or 0.314 seconds. So we've had a look at 3 examples of SHM, and the important thing to remember is that we need to find the equilibrium position first, that displacements must always be measured away from the equilibrium position, and that once we've set up the diagram with the positive direction of displacement set up, and that is also the positive direction for the acceleration.